Welcome to MEI Numerical Methods Convergence. In this video we'll be looking at numerical differentiation. Now the theory that we've developed for numerical integration in the previous two videos can be applied in a similar way to the numerical differentiation methods, and for the forward difference method it can be shown that the absolute error is approximately proportional to the h that appears in the formula, and that means that we would describe the forward difference method as a first order method, as the error is approximately proportional to h to the power of 1, and if each successive estimate is based on a width that is being halved each time, then we can say that the absolute error for one estimate is going to be half of the absolute error for the previous estimate, in exactly the same way that we saw for the numerical integration. In that case we had, for the trapezium method and the midpoint method, we had a constant k of a quarter, so this time k is a half, so otherwise it's exactly the same. And of course that would be described as first order convergence in exactly the same way as for numerical integration. And for the central difference method, which we saw converged faster than the forward difference method, it turns out that the absolute error is approximately proportional to h squared this time, and so that means that we would describe it as a second order method. And to find the order of convergence, this time it's actually the same as for the trapezium and midpoint rules, and so the absolute error for each estimate is a quarter of the absolute error for the previous estimate, and so that means we've got first order convergence again. So that concludes this video, and we'll be looking at numerical differentiation further in the next video.